So this was an incubator project that I'm happy to present El Paso today. So this project deals with the domain of space physics and space weather. So in the Earth's magnetosphere, we have a lot of charged particles trapped there. And this particle population is heavily coupled to the solar activity. So if there's a lot of activity in the sun, this particle population will be enhanced. And we are studying those particles because of the some interesting effects, which we call space weather effects. So the first one you should be all familiar with. So here I'm showing a picture of the aurora, or we also call it the polar light. And this is actually an image taken by myself earlier this year in Berlin. So I was quite happy to catch the aurora from my balcony at home. I can highly recommend it, was quite amazing. But there's also a not so nice side to space weather. So here I'm showing an image of an ESA satellite, and you can clearly see the damage done to the solar panel of the satellite. And it's also believed that the charged particles in the magnetosphere, which are responsible for the aurora, are also responsible for damaging our satellites. So it's very important to better understand these particles and how they change according to the solar activity. So the particles are measured by satellites. Orbits here. We are flying through the inner magnetosphere and having detectors on board, and they are giving us measurements of the particles. So the particles are actually organized by the Earth's magnetic field. We can approximate it as a dipole, as you can see here. And the interesting part for us is if two satellites are measuring the particles on the same field line. So the red curve here is a field line of the Earth's magnetic field, and then we have one satellite here flying at a low Earth orbit, whereas another one is flying on a highly elliptical orbit. And for some times there's one field line connecting both, which means they're measuring the same particles. And this is very interesting to us because we can do some interesting analysis here. So what this means is, when we get this data from the satellites, we always have to locate them in the Earth's magnetic field and do some field line tracing, which is quite numerically expensive. This task gets heavily complicated because the satellite missions are operated by different space agencies. So we have satellite missions from NASA, from Japanese JAXA, European ESA, and also Chinese organizations. And they don't really agree on which file format to use. So we have some data coming in .CDF files, other ones in CDF files, so this is a NASA file standard. And then sometimes we just get JSON or ASCII files. And also they're using different standards or no standards at all, which means the data has different units all the time, and also they disagree on the order of dimensions. So for example, sometimes satellite position is encoded in time, space, and the other times is space, time. So every time you want to look at a new data set, you have to look inside the file. Hopefully there's some metadata coming with this file, and then you need to do some pre-processing. So usually we need to do some time binning because we are not so interested in the high cadence data. Then there's some unit conversion we have to do, and generally speaking harmonization if we want to look at multiple satellites in the same study. And then there's also this magnetic field mapping and calculation of some derived physical quantities inside the magnetic field. And these are very time consuming. So we really just want to pre-process the file once and then load them again when we want to use them again. So this is now where my project comes in. So at GFC we are dealing with this kind of data for the last 15 years. So for each satellite mission we had developed mission-specific scripts to process this data and convert it to a unified standard. And all the scripts were available in MATLAB. And the idea of El Paso is now to take all the scripts, first of all translate it to Python, and then create a single framework which makes this, which streamlines this process. And hopefully, since the framework is open source, other research group will also adopt it, and we get all the benefits by using open source. I don't think I have to list them here in this meeting. So what our core framework looks like, you can see here. So it's still necessary for each satellite mission to write a small Python script, but it only has roughly 100 to 300 lines of code. So before El Paso, every mission-specific file had thousands of lines of code. So this got reduced to 100 to 300 lines of code. So we still have to provide information about what does the file contain and what kind of processing we want to do and how the process data should be stored. So the program flow of each of the scripts you can see here on the right hand side. Left column shows you what is provided by the user. In the middle we have the actual step performed by El Paso, and on the right is what is actually saved to disk. So the dashed boxes show you optional fields, whereas the solid boxes show you the mandatory steps you would definitely want to do. So we have some capabilities to download files. So you just provide an URL of an online repository, and it will download the data for a given time range, which gives us the raw data files. But this can also be provided by the user. So sometimes you just have a single CSV file, for example, you want to read in. And here we are now taking information provided by the user about how the variables are stored and which units they have inside the file. And we extract the variables from all the files we just downloaded or got provided from the user. Once we have all the variables, we have some processing function implemented in El Paso. So we get into time binning, other processing steps, and also these heavy magnetic field calculations. And these are just simple functions here. And then at the end, we can do the saving part. And I think I found this the most important thing. So here the user provides what we call a saving strategy and also a data standard. So the saving strategy just tells El Paso if you want to have monthly netcdf files, or should just everything go into a single file, or should the variables be split up in a specific way. And then the data standard tells El Paso which units to use to store the data and how the dimensions should look like. And it also does some sanity checks. So for example, if your flux measurements come with a time variable, then the time dimensions of both of these variables should be the same. So if there's a discrepancy, it will just error and tell you something went wrong. And then it saves all this process data, and with the data it also saves metadata, which I summarized in this table here. It's pretty much what you also usually see in nicely processed netcdf files. So we are storing the unit, then the source files, which were used for creating this data set, and then we have the processing nodes, which ensures the reproducibility. So it tells you when the data was processed, who processed it, and then also which version of El Paso was used, and you get the git commit hash to really see, so you can go and take a look which code was really used to process this process data. And then it also gives you an overview of which processing steps were performed on the raw data to get this final product. It was also important to do some verification if the calculation of derived quantities is actually correct. So here I'm showing a plot where we compare against the previously obtained results from the old code at GFC. It's actually not important what's really plotted here, but the black line shows you the previous results and red line shows you the new results by El Paso. And pretty much for all quantities, we get a almost one-to-one agreement. We actually found one or two small bugs, so I would trust now El Paso even more than the old results. And we also verified it against data provided by the satellite missions directly. So sometimes they give you some derived quantities. And here you can also see that we get pretty much a one-to-one agreement. So we can be pretty sure that the derived quantities are actually correct, which is always good to check. I want to end with showing the deliverables. So this was a 5-month-long incubator project, which pretty much paid my salary to develop this. And at the end, we have a GitHub repository. We also have, so it's licensed under Apache 2.0. We also have read the docs documentation. So this is just generated from the Doxygen inside the code. And we also submitted a paper to Earth and Space Sciences, so this is an AGU journal, and it's currently under review. You can see we have 5 forks on GitHub right now, so I'm aware that 2 other groups are also at least taking a look at it right now. I haven't had the chance yet to really present this in conferences, but I submitted an abstract to EGU and to other conferences later this year. So hopefully we can reach more people in the future. And with this, I will take questions. Thank you.